Expected, there is something that I can't explain it thoroughly, but I am still able to do this question. Okay, so let's do this question. So the velocity profile of a two-dimensional incompressible flow. So you have the two-dimensional x and y, and then incompressible, meaning density is constant, and therefore you know which equation you can use, which is this one, right? Two-dimensional flow and incompressible. If you remember, so we'll be using this equation. Okay. So how do we derive? Nonetheless, the fluid flow through a convergent nozzle shown here with a certain velocity in the only x direction. So this I hat. So if let's say you have a maybe plus yj hat, then you're talking about some velocity in the y direction also. Nonetheless, we are talking about x-axis. So this is it. So to tackle this problem, what I've copied is actually total derivative. Okay, this is the total derivative formula. Wow. Okay. So this portion. Okay. So this portion over here. Okay. So these things are the same as these things. Just are similar to this thing. Okay, not same. Are similar. But then okay. So what it means is that if you remember this one, when you're talking about compressible. So if you're talking about compressible, the previous formula was this one, right? It's the same thing. So when it's compressible, density is constant. So therefore, we can cancel this term away, right? And then and we are left with this three portion over here as shown here. And then when we talk about two-dimensional flow, we can actually cancel out these things. And therefore, um, this is how we have derived. This is how we cancel away this one also. You see, because certainly there may be some, partial density u over partial t, and then, yeah, you know what I mean. So, as I say, this term and this term are similar. This term and this term are similar, but I can't have an equation to describe how to derive until here. But nonetheless, we have two equations left over, which is this and this. And the difference are only such that there is a multiplication of the velocity vector to this equation over here. As you remember, this equation is actually kilometer cube per second. And if you were to remove, because it is constant, if you remove all the density, you are just talking about per second, which is a little no meaning. And then if you were to multiply per second with velocity, which is u is a certain velocity, so you have a acceleration. And this is what the question is asking. Find the total acceleration of the fluid particle along the x direction. So since we only have one x direction, we can actually don't care about the y direction because there is no y direction. So we can actually cancel this also. And therefore we are left over with this one over here, which is u partial x. And you know that the u, the velocity itself, is 1 plus x over L. And multiply by partial x, you get 1 over L. So if you want to check for the SI unit, okay, if you still doubt me, okay, this u, okay, it's meter per second, right? Maybe I should write over here, meter per second. And then this partial x, how do we do it, right? So it's meter per second divided by meter equals to 1 second. Okay, so this term has a per second type of SI unit. So with this, you already found our acceleration, which is this one over here. Okay, so this is A, the acceleration of the fluid particle. Okay, if you want to ask me how, I also don't have no idea. So now the part 2, okay, is if the particle is initially located at x equals to 0, find the location of the particle as a function of time. So we know that the hold on. We know that the velocity is dx dt, right? And the velocity itself is equals to 1 plus x over L, right? So just let you know, you need to understand what the equation is actually wanting to ask you. It's just saying that find an equation of the particle as a function of time. Okay, so in terms of time, when x is equals to 0, so you need an equation to describe x. Okay, you need an equation to describe x first, and then you sub in certain stuff. So we can use a separable equation. So you can hold a while. I just do out. So when I do a separable equation, I bring this dt up over here, and I bring this 1 plus xl down over here. So we have 1 over 1 plus xl dx. You integrate. Here you have a ln 1 plus xl because this is 1 over x in a certain sense. And then you also have to differentiate, integrate the inner one. Okay, so this will be 1 over L, so you have come over here. Okay, so imagine you have this equation. Okay, you want to differentiate. Okay, so you have to do a product rule. You will differentiate this, you will get 1 plus x over L dot with, and then you differentiate this part. Okay, now what it means. Okay, all the while there's no product rule in there. Okay, anyway, so if you differentiate this part, you'll get 1 plus x 1 over L1 plus xl, and then there will be an inner one. So you differentiate, you'll have L, right? Yeah. Okay, you have 1 over L, and this is actually L. Okay, so my mistake. So this should be L. Okay, I put wrongly. So never mind, I don't care this thing. So this should be L. So if you were to differentiate this one, first you differentiate this portion over here, you get 1 over 1 plus xl, and you differentiate the inner one, which is 1 over L. Okay, multiply by L, which is your equation after you integrate, right? So you have I hope you get what I mean. So this is just I sub in the wrong one, that's all. So this is actually L. So in other words, this is just pure math, that's all. And then you integrate dt, you get t, and then so everything would change. So hold on a while. So you have this, you just bring this down over here because they multiplied. So in other words, this one will come down. So this explains why we have over this thing over here. And then 1 plus xl. So now we do exponential. Okay, e to the power of ln is equals to 1, so therefore we have this one, and then this is this, and then you just rearrange, you just bring the minus, you just bring 1 over here, you have minus 1, you bring this L over here, eventually you get this over here. So this is the equation that describes your position with certain t, certain time, okay, and with certain length, okay, with certain length of this nozzle itself. So this is the part 2 of the thing. And then now talk about part 3. Part 3 is to find the acceleration of the particle as a function of time. Okay, so since we have this equation already, you can eventually make it derivative 2 times, you get an equation to describe the acceleration of the particle. Okay, so what I do is actually to hold on a while. So apparently when I expand this one, okay, I have this multiply out into here, you have this equation over here. So you just differentiate one time, you get e t l. The l is the constant, so you just differentiate away. That is 0. In other words, it's minus 0. and then if you differentiate the second time, you have TL ETL. Okay, so this is the equation that describes the acceleration of the particle in this formula itself, in this equation itself. So you may ask whether is this equation the same as this equation. So let me check it out for one. Actually, so an apology, this is actually 1 over L, because if you integrate t, okay, you integrate t over L, you are integrating t, right? So it's 1 over L. 1 over L is the constant, remember. So 1 over L times t, if you integrate t, you'll get 1 over L, right? So this should be 1 over L. And in fact, I said earlier that this equation is the same as this equation, and it is definitely correct. I actually prove it. So imagine we sub in, okay. So so the previous equation for A is actually this equation we derived using all the stuffs. But nonetheless, you can actually sub in the x. Okay, x is equals to this dude over here. So what I do is, so this portion over here is x. Okay, so this is x. It's the same thing as this. Just sub in back into here, divided by L. So you just cancel all of them. You'll get this thing. And then 1 minus 1 is equals to 0. So you have ETL multiplied by 1 over L. So you have this equation over here, which is the same as my equation over here. Okay, so this is just a proof, just to show you that they are the same. And nonetheless, for this thing, okay, for this thing, another approach is actually to straight away differentiate this one. Okay, it is pretty much straightforward. Okay, what I mean is actually because as you say, a two-dimensional incompressible flow. So when you talk about incompressible flow, there will be no density changes. And since you also know that there is only one direction, x direction, you can straight away differentiate one time to get the acceleration, that's all, which is what we actually is doing. Okay, just that it's a little complicated talking about this dude over here. Okay, when you're talking about why do we multiply the velocity to this system? This is the thing that I have no idea what the hell. So nonetheless, this method only apply when you're talking about one direction, and then talking about incompressible flow, and then yeah. So I know talking about So this is a little tricky, but just to let you know, there's another approach, but don't do this. But nonetheless, you can also do this approach, but straight away calculating the x position first, and then you integrate differentiate 2 times to get the acceleration of the particle at certain portion over here. So I'll just confirm with you again how this comes about. Hopefully I can confirm with you, and then I also have a video to introduce you to the thing. So this is the thing. I mean, this is I'll just tag along with the playlist so you can actually watch with it. It's just how different. These are the things that is not being described over here. Okay, not described over these places. So I hope that I can give you a quick understanding of that. And this will end my portion over here. This whole stuff. So one confusion is always this equation. So from here you can actually understand that I have struggled quite a lot with this dude, and struggle quite a lot with how this thing comes about into here. So yeah, so I'll see you in the next lesson. Bye bye.